quantum mechanics, computation, and algorithms. So, sir covered almost all very large topic, all the topics, our quantum mechanics, quantum gates, algorithms, and all the in a very short available time, because we have only 1 hour, maximum 1 hour time. In 1 hour time, covering all these things is very difficult, but sir covered almost all satisfactorily, give all the topics, covered all the topics during the second day. Thankful, sir. And for all the above two sections, is engaged with almost approximately around 200 participants. All participate interesting with more interest. And however, the registered participants are 550, more than 550, but only 200 participants are seen on the call. So I request all the remaining participants try to participate in the FDP. And thank you all the participants and all of you for your very good response and valuable support during this 2 days. And today marks the final day of our 3-day FDP. So we are pleased to have Dr. R. Muthuganeshan sir today, Research Assistant Professor at SRM Institute of Technology, SRM University, and Tamil Nadu. Sir will deliver a talk on entanglement and its applications. So really this is the advanced topic, I think, and we are very eagerly, we are interested to to hear the talk and to discuss doubts with the sir. We are very eagerly waiting for that. And now I request my colleague Sri Y. Chaitanya sir to present a profound profile of Muthuganeshan sir. Chaitanya sir, please take the session.
Thank you, sir. Good afternoon to all dignitaries, participants, and dear colleagues. It is my privilege to introduce today's esteemed resource person, Dr. R. Muthuganeshan sir. Dr. R. Muthuganeshan sir is currently serving as a research assistant professor in the Department of Physics at the SRM Institute of Science and Technology. In addition, he has been working as a postdoctoral fellow at the Czech Technical University from February 2022. He obtained his PhD in physics from National Institute of Technology, Tiruchirappalli. His doctoral thesis is titled Fidelity and Measurement-Based Quantum Correlation Measure for Bipartite States. He worked extensively on fidelity-based quantum correlations and measurement-induced quantum correlations in bipartite systems. His areas of research interest include quantum resource theory, open quantum systems, and quantum information processing in condensed matter system. He received the MHRD, Ministry of Human Resource Development Research Fellowships. He also qualified GATE in physics and the Tamil Nadu State Eligibility Set, that is SET. Dr. R. Muthuganeshan sir has authored more than 38 peer-reviewed research articles published in reputed international journals, many of which are indexed in the SCI database. His research contributions span quantum coherence and fidelity-based measures, measurement-induced non-locality, quantum correlations in noisy and non-Hermitian systems, and spin chain models in condensed matter-inspired quantum information. He has presented his research work at several prestigious national and international conferences, including Asian Quantum Information Science in Singapore, Quantum Information and Measurement OSA, the DAE Solid State Physics Symposium, the Harish Chandra Research Institute, the Raman Research Institute, and scientific events conducted at the Fraunhofer Institute and the University of Geneva. In addition to his academic contributions, he has actively participated in professional service activities. He served as a vice president and president of the OSA student chapter at NIT Tiruchirappalli, volunteered in organizing national and international conferences at and seminars and acts as a reviewer for multiple international physics journals. With this brief introduction on behalf of FDP Organizing Committee, I once again extend a warm welcome to our esteemed resource person, Dr. Muthuganeshan sir, and I request Dr. Anjaneyal sir to take over the session and proceed further. Thank you.
Thank you, sir. Thank you, Chaitanya sir, for your nice introduction about Dr. R. Muthuganeshan sir. And now is the time. So I hand over the session to Dr. R. Muthuganeshan sir to deliver the lecture on the entanglement and its applications. Muthuganeshan sir, please welcome, sir. Please take the session.
Yes, sir. Thank you, sir. Thank you very much. Thank you very much for your nice introduction as well as bringing me here for the this wonderful conference. As also, I am very happy to one part of the part of your National Science Day celebration in this occasion. So, especially I thank our principal and head of the department of our physics department, Bapatla Engineering College. Thank you, sir. So, actually, my presentation is on entanglement and its applications. Is it visible, sir? My slides in full slides will move. Okay, then I start. So before starting my presentation, I would like to give some important reference for the quantum mechanics. So my first two book, Quantum Mechanics by Nurdin Jetli and the Quantum Mechanics by Matthews and Venkatesan, are a nice textbook for the beginners of quantum physics. Those who are started to read the quantum physics, they can refer the first two books. And the second two books, Modern Quantum Mechanics by J.J. Shograi and Principles of Quantum Mechanics by R. Shankar, are the slightly advanced topic. It is more interesting textbooks. So another three textbook related to the quantum information and computation. Those who want to go to the details of quantum information, please get into these three books. So these are three nice books. So with this, I start my presentation. Well, my first slide. So the quantum technology is a common research field for all the people, science and engineering. Especially the quantum technology developed by the physics and mathematical people to develop the foundations of quantum technology, especially introducing our many concept of basics of basics of quantum physics, developed the advanced level of quantum mechanics, and the computer science people developed the algorithm for the different algorithm and in the how we can realize in the quantum level. So the chemistry people, many of the people involved to realize how we can realize in the different qubit system and for the different mechanism. And not only that, apart from that, the science background, there are few like ACE or in triple E backgrounds. So people also working involved in the development of quantum technology. So what is quantum information science? The quantum information science is the combination of information theory and quantum mechanics. The information theory exploit the principles of quantum mechanics. Finally, we combine that quantum information science very in the advanced level. So these are some important, remarkable discovery in quantum technology. So the first point of this development of quantum technology is in 1935 due to the publication of Einstein and his co-worker. They have shown that the quantum mechanics are not correct. So due to this the paradox, the people coined the name the quantum entanglement. In 1935, Schrödinger and Bell are introduced the concept of quantum entanglement. So this is the remarkable phenomena. So this is the reason for we are sitting to discuss quantum technology. After that, in 1964, the Bell introduced the inequality to contribute whether the system behave as a quantum system or classical system. We can classify with the help of inequality. So we can discuss in later. So after that, 1980, Paul Binet introduced the Turing missile model, Turing machines based on the classical theory. So after that, he introduced the concept of quantum mechanics in the computational methods. So in 1982, the Richard Feynman first introduced we can simulate the problem or we can solve the quantum problem with the help of quantum mechanics principle. In 1985, they theoretically they have developed the universal quantum computer model. That means whatever we have the quantum model, computer model, they have developed theoretically with in 1985 by David Strach. And after that, in 1993, so Charles Planet and his co-workers, they have introduced the concept of quantum teleportation. That means we can transfer information from one place to another place with the help of entanglement. So after 4 years, the Boehm study demonstrated how we can realize this teleportation process with the help of entanglement in using the photonic systems. In 1998, Nielsen and Swang, they have introduced the quantum computer. So based on the 2-qubit system, so the NMR qubit means based on the nuclear spin. They have demonstrated NMR. In 2005, they have introduced the concept of quantum bytes. So byte means we have the eight bits. So quantum byte series of eight qubits. So using this 8 qubits, they have analyzed another one set of a quantum computer model. So in 2007, a company named is called a D-Wave system. They have commercially designed a quantum annealer with a 128 qubit system. So in 2011, John Braskill introduced the noisy intermediate scale quantum. So in general, the quantum system always it is coupled with the environment. So it is always the noise is present. So due to this noisy effect, they have identified how we can realize the quantum mechanical effect with noisy. So then in 2012, Wineland and Karochi introduced they have demonstrated how we can control a single quantum atom. So they have for this the experimental demonstration, they got the Nobel Prize in 2012. So after that, 2022, there is important demonstration of violation of Bell inequality. This is the remarkable experiment. Again, they got the Nobel Prize for the this experimental demonstration in 2022. In 2023, so they have shown that the IBM and Google and Chinese Academy of Sciences group of people, they have identified the logical qubits and they have improved the fidelity. That means we have during the noisy process how we can improve how we can correct the error and we can improve the fidelity. In 2025, recently in the last year, they have demonstrated and realized the quantum tunneling in macroscopic level. If you check in 2012 to 2025, within the 15 years, so we have got the Nobel Prize for the quantum technology field. Okay, so 3 Nobel Prizes. The 2025 also the demonstration of macro realism quantum tunneling experiment, they got a Nobel Prize. So these are some important, remarkable discovery in quantum technology. So with this, we can start about the classical information theory. So in thermodynamics, we have studied about the entropy. So entropy means a measure of disorder in the physical system. So for example, gas or any other physical system, if we consider the amount of molecules are randomly arranged, that random arrangement is defined by the entropy. So in classical, in information theory, that entropy and information is related. Okay, so if I have less entropy, then we have the less information. What this information theory deals generally, if it is information means we have some kind of data or any video signal or audio signal, something we have to use to exchange the information. So that means we have to communicate some kind of information from one place to another place. So this information theory always deals about the exchange of data. So that communication should be efficient. That means we have to we have to exchange the data very efficient and more secured way, because of it nowadays we are in the digital world. So we have to use the communication more secured, and that communication should be also reliable. Okay, so in classical information theory, so we represent the data with the help of bits. So in binary numbers, we have the 2 bits, one 0, another one is 1. So this is we have realized during the logical gate experiment. If you have the high output, we have the binary bit 1. If it is we have the low output or 0 volt, we have the binary output as 0. So this we have the 2 binary input. So with the help of this two binary input, we can label or represent the information in classical information theory. Okay, so generally bits we can operate it with the logical gates. So we are familiar in the logical gates with OR gate, AND gate. So these are the gates we can use in the classical computation. So here there are some important concept in. So if we consider the classical information theory, we can clone the bits. Okay, that means we can generate the bits. Another one is a bit have the long lifetime. So generally, if you have optical, if you have electrical signal, until we have to stop the or to cap at a particular time, for example, say 8 a.m. So sharply or all the time you will get the bus at 8 o'clock. Suppose if you are any one of the day your bus is very late or 5 minutes late, then you have a question. The bus getting late is very less probability. Then we have the questions: is there any traffic jam? Is there any strike? Or is there a schedule change? So what is the problem? That kind of big questions we can arise about the that event. From that questions, we can get more amount of information. That's why. So whenever we have the less probability of event, then we will get the more amount of information for particular event. Okay. So with this, we can identify that if whenever we have the less probability of the event in quantum mechanically, then we have the more amount of quantum information. So this is Moore's law and its limitations. So this Moore's law, it is introduced in 1965 with they states that in the integrated chip every 2 years the number of transistors is doubled. Okay, so what will happen if you increase the number of transistors in the integrated chip, the computing ability of the device and the communication efficiency or everything is the efficiency of the device is get enhanced. But the problem is, so in the year of 2020, what happened? This the natural end of Moore's law. After that, what happened? That the transistor in the integrated circuit is not doubled; it is exponentially increased. So especially after the 2020, the number of the transistor in the given circuit or integrated circuit, the number of transistors is exponentially increased. Then what happened? So because of this, this arises due to the small size of the transistor. So due to the development of semiconducting technology, so what will happen? This transistor size is extremely small. Okay. So for example, currently the transistor size is 4 nanometer size. So less than 4 nanometer. Okay. But you just think about if it is 4 nanometer, then naturally what will happen? So the transistor size is very small. Then we have to enter into the microscopic world. That means we have to exploit the principle of quantum mechanics. Okay. So this is the first reason why we are need the quantum technology. So nowadays we are using the micro transistor with sizes very less than 4 nanometer size. Okay, due to the small size, what will happen? So due to the small size, the quantum mechanical principle naturally starts to play the game. Okay, so then the first one is, so whenever we enter into the microscopic scale, what will happen? The measurement observables. Okay, if you observe any physical quantity, it is not reliable. Why? So because of Heisenberg uncertainty principle. Whatever the physical quantity, if you measure in quantum mechanics, it is not accurate measure. There is always some amount of error due to the Heisenberg uncertainty principle. Okay. Another one is if you use the more number of transistors, what will happen? The transistor will produce the heat. Okay. For example, if you charge our smartphone, what will happen? Nowadays we are getting more heating because of there is more number of transistors is connected. So due to this heat produced, what will happen? The heat produced by the one component, it will affect the performance of the nearby component. Okay. So then what will happen? If the heat of the device is if we increase a lot, what will happen? The information is automatically destroyed. Okay, then already I have explained the logic gates are irreversible. We cannot get the nature of the input condition with the help of output condition. Another one is the computational speed. So yesterday, Professor Sanganarayan explained some of the problem we have to solve if it is any problem in the order of the exponential n, then it is very difficult to solve. Okay, that kind of problem we can solve with the help. Second thing is the transistor will produce the heat. That heat will be affect the information. And another one is the logic, the irreversibility of logic gates and computational speed. Okay, due to this, we have to go for the quantum computations. So these are the some basics. We already everyone familiar with the Euclidean vector space. So generally, if you have any vector, so in the vector space we have the different vectors. So if you add two vectors, we will get another one vector, or if you multiply a scalar by a vector, you will get another vector. Okay. So the thing is, if you consider the vector space, that is called, we call it as a linear vector space, it will satisfy these four axioms known as associative and zero, the existence of zero vector and the existence of inverse vector. Another one is the commutative. So this four axiom will satisfy a linear vector space. Okay, so why we are introducing this linear vector space? Because we are going to use another one linear vector space is called a Hilbert space. It's a complex vector space. So again, it consists of different vectors. So it will follow the same axioms. But only the thing is, what the vectors in the Hilbert space are the complex vector. That means we have some real and imaginary numbers. Okay. So that we can represent with the help of different notations. So the only thing difference is if you consider the linear vector space, our like a position momentum or the real vector, in the quantum mechanics we have the complex vector. So if you consider this, what is a quantum computer? If you computer, the quantum computer is a machine that performs the operation or calculation, any processing task with a law based on the law of quantum physics. That means the behavior of particles or any device components. So it would follow in the subatomic level. So the important concept is the state of a system. So we have to define the state of the system. That means if you have any physical system, we have to represent as a qubit. Then in order to represent the qubit or system or the behavior of the qubits, so we have to understand the concept state of the system. The state of the system means the available information on the properties of the system. That means if whatever you consider the property, how much amount of the information is available about the property of the system, that will represent the state of the system. That the state of the system we can define with the help of a state vector or a wave function. So suppose if we have a discrete energy values, we can, in discrete system, we have described with the help of a state vector. The same physical system, if it is in the motion or any movement, we have to describe with the help of wave function. So because if we consider any quantum particle in the motion, if moving with some velocity, so naturally due to the de Broglie concept, de Broglie matter wave concept, that particle having the wave property also. Then we have to, if a particle having the motion, then we have to represent with the help of a wave function. Generally, a state of the system we can represent it by a complex function or a vector. That we can write psi is equal to sum over I equal to 1 ci pi I. So this pi I are the complex vector in the Hilbert space. So centrally, if you consider the previous one, so there is the linear vector, real vectors in the linear vector space. This pi I is a complex vector in the Hilbert space. So this complex gives the information about the physical system. Okay. So this Ci is the normalization. Ci is the probability coefficient. If you find the total summation, it is equal to 1. This is due to the conservation of probability. Okay. Another one is we have the different notations. If you consider the A, B, C, or some basis vectors, so that we can represent as we can call it as a ket. So that ket we can write as a column matrix. That means A1, A2. That means we have to give the representation of column matrix. So which is equal to AI. So this AI we can calculate from this inner product. So I will explain in the next slide what is the inner product. So another one is it is this Hermitian conjugate. That means if you find the complex conjugate with matrix transformation, we will get the bra vector. That means, so we were get vector, it is a column matrix. If you consider the bra, that is after finding the complex conjugate matrix transformation, so it become a bra vector, that is a column matrix. Okay, so these notations. So the first one is vector, get vector. Another one is bra vectors. So then this symbol is called inner product. Another one is tensor product. Then inner product between the state. Okay, so qubit, the quantum bit. So generally in physical implementation of your qubit, use the two energy levels of this atom. Okay, so for an example, if you consider the electron, if you place it in a magnetic field, it will have a 2 degree of freedom. That means it will split into two spin particle, one is either spin up or spin down. Then it has a two energy level. This kind of level, energy level, we call it represent as a qubit system. So we have a different energy value E1 and E2 that we can represent the state ket0 and ket1. So that we can represent ket0 equal to in the column matrix 1 0. Similarly for ket1 we can give the 0 1 1. So this is, yeah, we have the two level system. So I have then it is called the Hilbert space with a dimension of 2. So this we can write as the combination of superposition of ket01 state psi equal to alpha times 0 plus beta times 1, or in matrix notation we can write the column matrix of alpha and beta. So here this alpha beta are the complex numbers. It will give the probability coefficient. So if you find the summation of alpha squared and beta squared, it becomes a 1. Okay, then what is the physical significance of alpha and beta? If you find the modulus of alpha squared, it will give the probability of finding the state in ket0. That means if you find the modulus of alpha squared, it gives the probability of finding electron in the state ket0. Similarly, if you have the beta squared, if you find the value of beta squared, it gives the probability of finding electron in this level ket1. Okay, so this is the spin-off particle. Whenever we have the spin-off particle, we have the state represented is ket0 plus ket1. Okay, so this is for the common for all spin-off particle like electron, proton, neutron. So any atoms with having the spin-off particle like sodium or sodium, potassium, like this kind of atoms also having the outermost orbital having only single electron. That kind of atom also we can represent as a qubit as a, so this way, psi is equal to alpha 0 plus beta 1. Okay, so then the important difference between the bits and qubit is, so the qubits we can exist in the superposition. Okay, so that means ket0 plus 1, that is the superposition of qubits. So here we have the power of quantum computations comes from that superposition principle. So whenever we have the combination of superposition of qubits ket0 1, so with the probability coefficient alpha and beta. So here the thing is, in classical computation, if you have the two bits, we can store the 4 information. But here you can realize if you have a single physical system, for example, single electron. If you have the single electron, we have the linear superposition of ket0 and 1. So for the all possible values of alpha squared plus beta squared, it is equal to 1. We can store the one information. For an example, if you take a beta squared is equal to 0.5, so then it will have the alpha squared is equal to 0.5. For alpha squared is equal to 0.5, we can store one information. Then if you set a modulus of beta squared is equal to 0.51, so again, we will have a possible one valid quantum state. We can store one more information. For another value, 0.511. So again, we have another set of quantum states. So likewise, for all possible values of beta squared, we can realize a valid quantum state. We can store one information. So then we have, if you consider your single two-level system, we can store more number of information in a single system. So due to this more capacity of memory and other processing, and super principle, we have the enormous power of quantum computations. So this is the reason we have the more power in the quantum computation. The reason is, so another one is, if you consider the superposition of principle for the principle of electron, if you consider this, another one is 1. If you consider the superposition principle, the direction of the spin will be in between ket0 and 1. So in generally, the energy values between ket0 and 1 is forbidden because of the energy levels are quantized in quantum mechanics, but the energy level maybe it's 0 plus 1. But if you measure the quantum spin, what will happen? So after this, any one of the state will be available with the probability of, if after the measurements, what will happen? The system will collapse into either ket 0 or ket 1, depends on its probability. Okay. So generally this quantum bits, it is classical bits. Okay. So we can measure, we could not measure it completely because of it is in quantum mechanically, all the phenomena is probabilistic one. So we could not measure the quantum bits accurately. So we can measure partially only. After that, if you measure the system, what will happen? It will collapse into another state. Okay. So for that principle is called one-even collapse postulate. So what this principle states that if you measure the quantum system, what will happen? It will collapse into any one of the eigenstate of the system. Okay. If the electron in the superposition state get 0 plus 1, if you measure the electron property, that the system will collapse into either ket 0 or ket 1. So that is the reason, that is the meaning for this one-even collapse postulate. So then another important thing is we cannot copy the information, quantum information. So if you consider if you classical computer or classical information, we can make copy and we can paste into another devices. But in quantum mechanics, we could not copy the data. That means we cannot clone the qubits. Okay. So, but in bits, we can clone the data and we can copy the data. But in quantum mechanically, we cannot be copy and no cloning theorem is due to the no cloning theorem. We cannot copy the data and we cannot erase also. Okay. So then this is another linear superposition of the state 1 by root 3 0 plus square root of 2 by 3 1. So then in that case, if you find in that state, the system having the probability 1 by 3 to in the state ket 0. So under this the system be in the state 1, the probability is 2 by 1. So generally this probability conservation, if you find the total probability, the total probability is 1, then finally you will get the total probability is summation of A equal to 1. So this is some of the implementation of qubits. The first one is photon polarization. If you consider the electromagnetic propagation along x direction, so the photon may be in x, the polarized in x and y direction. Then we have the two types of polarization. So here we have the horizontal and vertical. So horizontal having the less amount of energy, then we have the ket 0, and another one is ket 1. So similarly, we have the spin of particle like trapped ions like sodium or electron spin or nuclear spins. So these are having the spin of particles like trapped ions. So the NMR qubit system is a nuclear spin. Another quantum dot is atomic system. Okay, so this kind of system we have the two energy levels that we can label as a ket 0 and ket 1. So another one is a QD, the superconducting quantum interface devices. So that interface devices we have the qubit system. It is based on not based on this energy. It is based on the degree of freedom, the direction of the spin component. Okay, so if you consider the spin of direction of the current, we can have. So if the direction of the current, if it is left direction, we have the qubit 0. In another direction, we have. Okay, so these are some important qubits. Nowadays, it is available for the experimental realization. So under the very extremal conditions like high pressure and very low temperature, we can realize this kind of qubits with the further very shorter duration. So because of all the qubits having the lifetime is very less. So another one is so this is again the representation of atomic qubits. So if you consider this representation, we have in the center we have the nucleus, and we have the different energy level, the ground state and the excited state. In the ground state, we can represent as a label as a ket 0, and the excited state is ket 1. Okay, so if you consider any atom, the electron in the ground state, so if you give some amount of optical input or any kind of form of energy, it will absorb and it will go to the excited state that we can label as a ket 1. So in some of the case, what will happen is the transition is between the ground state and excited state. So then the state may be in the superposition of ket 0. That means we can find the probability of system. We can find the property of the system in both ground state and the excited state. So that we can represent as alpha 1 0 plus alpha 2 1. Okay. So this is with a probability of modulus of alpha 1 square plus modulus of alpha 2 square. So here another one important thing is the information no broadcast. That means we cannot telecast the information from one place to another place. So this is another the higher dimension system. So the previous one is qubit is a two-level system. The Q treatment. So we have the three-level system that we can have label get 0, 1, and 2. Okay. So with a different energy level E1, E2, E3. So here we have the basics vectors V1, V2, V3 are the here we have, then we can write the representation of the state as psi equal to alpha 1, 0 plus alpha 2, 1 plus alpha 3, 2. Okay. So in the column matrix representation, we have the column matrix alpha 1, alpha 2, alpha 3, and this V1, V2 or the V3 are the basis vector. So these three vectors will span the three-dimensional vector space. So the next one is this energy level of harmonic oscillators. So if you consider in the harmonic oscillator, we have the different energy levels. So if you consider the first two levels, we can realize the qubit. If you consider the next three levels, we can realize the qubit. Likewise, we can consider. So if you based on this number of energy level, if it is 2 level, we can realize the qubit system. If it is we have the 3-level system, we can realize the QTET system. Okay, so this QTET system is a three-dimensional system. We have the three basis vectors. Okay, the next important concept in quantum physics is inner product. That means we have to write. So this is the representation. So UV. Okay, this is the inner product representation. Generally, if you find that these are the vectors, if you complex vectors, after finding this inner product, it will be a scalar quantity or a complex numbers. Okay, so if you find the two vectors, inner product is 0, then we call it as the vectors are orthogonal to each other. So if in the classical case, if you have two vectors, if you find the inner product A dot P equal to 0, then we have the vectors are orthogonal to each other, means the vectors are perpendicular to each other. But here is the concept is different. If it is orthogonal to each other, means both the vectors are mutually disjoint. Okay, there is no similarity between two vectors. That is completely different vectors. Okay, so that is the meaning is the orthogonality is not a perpendicular to the perpendicular. So here, if it is orthogonal, means the vector u and v are completely different. So then, if you find the inner product of the same vector, we will get the norm of the vector. The norm of vector means it gives the length of the vector. So from that length of vector, we can analyze the properties of the physical system. It is one of the important quantity in quantum mechanics is the inner product that we give a complex scalar quantity. Another one is outer product. So in the previous case, if you find the inner product, we will get the scalar quantity. So here we have outer product. So the outer product means we have the two vectors. First we have psi and another one is phi. We can define psi is equal to AB and phi vector is equal to CD. If you find the outer product, we have to write psi and phi. So it's calculated way, we can write this as AB. So this is a pi is a bra vector. Then we have to find out the complex conjugate and we have to take that matrix transpose. Then finally, if you find the outer product, you will get a matrix. Okay. So in the previous case, in the inner product, you will get a scalar value. So here we will get a operator or is called a matrix. Okay. So this is the resultant matrix. So in many cases, in order to construct the quantum mechanical operator, we have to use this outer product. So then, matrix representation. Suppose if you have a Hilbert space, we have the different basis vector. So if you, for an example, if you have a two-dimensional vector space, ket 0 and ket 1, the basis vector, we have only two vectors. If you consider the three-dimensional vector space, if you have the basis vectors are ket 0, ket 1, and ket 2. So these are the basis vector. Now, if you consider the n-dimensional space, we have the different basis vector like it starts from ket 0 to up to ket n minus 1. So if then the important relation is called a closure property or completeness. So it gives the summation of, if you find the sum of all the basis vector in the outer product form, it will be reduced to the identity of ui. Then if you substitute I, we will get this relation. So if you combine ui and psi, we will get ci. The ci is nothing but constant. So this ci, if you arrange in the matrix column matrix, we will get the matrix form of your psi. Similarly, we have the matrix form for the operator also. For the matrix, if you kind of matrix A, so we have to write I times A and I. So then for each I, we have to give the basis summation with the different indices. So finally, we will give the different matrix representation. So that matrix representation, we have to find out the inner product of operators for the different basis vector ui and uj. So if you find the ui uj for the based on the different basis vectors, we will get the different matrix elements. Then we have to arrange in the matrix form. So suppose if we have the basis, if you consider any Hilbert space, the basis is not unique one. So for a given Hilbert space, we can generate more number of basis vectors. So if you consider in the first case, we have the basis vectors are ui. So now in the next case, we can consider some vi. It is called another basis vector. If you find the matrix representation of a in basis u and v, we have the different matrix. Okay, that means the matrix representation in the basis u and the matrix representation of a in vector v is having the different matrix. Okay, that means the operator is the operator is different. We have the different operator in different bases. It is not a unique representation. Okay, generally the operator have some general properties, but it will be maintained in the properties. But the matrix representation will be different in the different bases. So, for example, if you have this 2 by 2 operator matrix, so for that operator we can represent as the matrix A. It is equal to the first term ket 0 A ket 0. So this is the first element A. Similarly, we can define B equal to ket 0, bra 0 A ket 1. So for C equal to bra 1 A 0. Similarly, we can define all the matrix element. Okay, that means we have to find out this value of operator, the matrix element for the given basis 0 and 1. From that values, we can construct the matrix form of a given operator. So this is another one important operation, the trace of an operator. So if you consider any operator, this operator we can represent it by a square matrix, whether 2 by 2, 3 by 3. So based on the dimension of the Hilbert space, we can give the different dimensions, like 2 by 2 or 3 by 3 operator. Then the trace of operator mean it gives the summation of the diagonal elements. So for the first case, so we have the 2 by 2 matrix, the diagonal elements are A and D, then the trace of A equal to A plus D. So in the second case, we have the 3 by 3 matrix and the diagonal entries are A, E, I. So then the trace of matrix B is A plus E plus I. Okay, the trace of operator means the sum of diagonal element. Okay, so here we can write, similarly we can write matrix A. So if you consider this matrix representation here, so the trace means we have to find out the sum of the diagonal element. So that means the first one. So here we will get so the inner product of a bra ui a ui. So that means we in both the bra and vector we have the same vector. Then we have the trace of operator. So the trace of operator is more important concept in order to find the expectation value or any measurement outcome. Or for the many concept, the trace of operator is more important concept in quantum mechanically. So the next one is the Hermitian operator. So the Hermitian operator is most important. So because of it, if you consider the classically, so we have the position, momentum, and other physical quantities, we can represent it by a real quantities. So it's the same thing we can represent in quantum mechanics, but the thing is we have to represent as a Hermitian operator because of the eigenvalue of the Hermitian operators are real. Okay, because if you consider the quantum mechanically energy operator, it should be real. Maybe it can be either positive or negative, but so it should be a real quantity. That is the reason why whenever we represent the quantum mechanical operator, so always it should be a Hermitian operator. Okay, then a Hermitian operator means what it means. So if you find the matrix and it is transpose, that means the transpose means the combined operation of complex conjugate and matrix transpose. Then if it is if we consider matrix A, it is equal to its Hermitian transpose, then it is equal, then we call it as the matrix is a Hermitian operator or Hermitian matrix. Okay, so these are some important properties of the Hermitian operator. So it will these properties are helpful to learn some important problems and solving some physical problems. So for example, if you have the matrix A, B, C, D, okay, then if you find that complex conjugate and we have to transpose, then if we will get if it is both are A and A transpose are equal, then we have A equal to A transpose. For in that conditions, so if it is a Hermitian operator, the diagonal entries should be real. That means ADR should be always a real quantity. And if it is here, the B and CR, it is complex conjugate. That means P equal to it's C star, it is complex conjugate. Then only it will satisfy the Hermitian conditions. So this is one of the example of Pauli spin matrices is a sigma Y matrix. So that we can, and if you find the Hermitian conjugate, complex conjugate, you will get Y dagger equal to Y. The sigma Pauli spin matrices are Hermitian operators. So then always in quantum mechanics, we have to represent all the physical observable in terms of a Hermitian operator. Okay, that means this is the Hermitian conditions. The diagonal entry should be real and the off-diagonal element should be equivalent to its complex conjugate. So another one important operator is unitary operator. Why this is important? So in all the quantum operations are we can represent it by unitary operator. For example, if you define any quantum gates, it should be a unitary operator. Or if you apply a time evolution of a quantum state, that operator is also a unitary operator. So all the quantum operation we can define with the help of unitary operator. So here we have the important property U dagger or U dagger U equal to I. So that means the U dagger, that is the complex Hermitian conjugate of the unitary operator, it is equal to its inverse. So this property gives the reversibility of quantum mechanics. So while discussing in the AND gate, we have the different 3 input gates. 3 output is same for the 3 different input. So here we have here we can understand the quantum importance of quantum gates. Okay, so if you have any output conditions, from that output conditions we can identify the nature of input condition due to this reversible condition of unitary operator. Because of U dagger equal to I, that is U dagger equal to U inverse. Due to this property, we can identify that the important properties of quantum mechanical system. So the next most important concept in quantum information or quantum computation is operator. So in most of the case, we can represent by this get 0, get pi. So the next one is generally that based on the pure, consider this of pure vector, few states, then we can few states, then we can call it as a mixed state. So this is this kind of summation is called a convex combination. So it is different from the superposition principle. Okay. So here also we can give the conservation of probability sum over pi equal to 1. So here we have the probabilities of pi. It is a classical nature. So if you consider the few state, we have the probability modulus alpha squared and modulus of beta squared. It is a quantum. The probability is a quantum mechanical nature. But probability is a quantum mechanical nature. But in mixed state, we have the probability pi. So see here we have the products pure state psi a. Similarly in the pure state psi a. Similarly in the product state, we have the some other probability coefficient like alpha beta. That alpha beta will give the quantum nature probability of quantum mechanical nature, but this pi will be the classical probability. It is slightly different. It is follow the quantum classical principle. So then if you have the density matrix, it is not a purely quantum mechanical one. So we call it as a hybrid. That is a mixture of classical and quantum nature. So that's why we call it as a mixed state. So whenever we have the uncertain situation, that means we have the depth indefinite probability, that kind of situation we can represent it by a mixed state. So here also we have the conservation of probability trace of rho equal to 1. So generally the mixed states are not projected. That means rho square not equal to 1, not equal to rho. So due to this property, so whenever you find the trace of rho square, it is always less than 1. So for an example, if you have a rho is equal to the equal combination of get 0 and 1, it will be a maximally mixed state in a 2-dimensional Hilbert space. Then if you find this, we will get to the purity or the trace of rho square become 1 by 4. It is very less, 1 by 4 is a very less value. So this is the geometrical representation of qubit system. So if psi is equal with that, we can write this mathematical expression in matrix form. We have another representation of plus r dot sigma. So this is in the matrix representation. If you consider this geometrical representation, we can represent a three-dimensional sphere as the points in the three-dimensional sphere. We can have a quantum state. Okay. So for an example, if we have for possible all values of theta and pi, we can realize the quantum state. So okay, if you consider the magnitude of vector r equal to 1, we can realize a valid pure quantum state. Okay. That means if you have a sphere, so on the surface of the sphere, on the points on the surface of the sphere will represent a pure state. So the points inside the sphere will represent as a mixed state. So the point at the center will be a maximally mixed state. Okay. So this is the matrix geometrical representation of a valid quantum state. This is for single qubit state. So similarly, we have the geometrical representation for the 2 qubit also. So here this projection operator, it is we can represent as a pure state. So this is one of the important quantum mechanical operator. So then this measurement. So this measurement, if you measure any physical property of the system, so what will happen? The P of AN is the outcome of the measurements. So it gives the P is the probability to get the outcome is AN. That means if you find the measurements, so we will get the measurements that we can write in the form of a trace of Pn. That is, the Pn is the projection operator, and in the measurements we are taking on the state rho. Then finally we will get the outcome is AN. That outcome we have the probability is P. Okay, so this is the general form of how we can take the measurements. So generally, we have the different measurements that we can write as a MM. So that we have, in some of the case, what will happen? So the sum of the operators, it should not follow the conditions, the unitary operations like U equal to U dagger. At that conditions, we could not find the trace of rho is it is not equal to 1. In order to normalize the state, we have to divide the factor trace of M dagger, M and rho. So this is whenever you take the measurements on the quantum system, the resultant state will be, the result is this one. So that is rho equal to P and rho Pn divided by the trace of Pn rho. Okay, then next is tensor product. So far we have discussed about the single qubit system. Next we go for this 2 qubit system. So in quantum mechanics, we always have we have more number of particle system that we can extend into the with the help of tensor product. So the H is the joined Hilbert space. The H1 is correspond to the Hilbert space of the particle 1, and H2 is the Hilbert space correspond to the particle 2. So that the dimension of the extended Hilbert spaces, that we have to multiply the dimension of the first Hilbert space and second Hilbert space. Now we have the chi, ket pi is the state of the one particle, and chi is the state of the another particle. Then from that 2 particle, we can generate a composite state, that is a pi particle or composite state, that we can write psi equal to pi tensor chi. Okay, so this tensor product, we will have that pi tensor chi equal to, we can define the pi vector equal to AB and chi vector equal to CD. Then after finding tensor product, the result will be, we have to multiply the each element of first vector by the vector. Okay, so pi vector we can define A, that the A we can multiply by the vector of the second particle. Then it will become AC, AD, then BC, BD. Okay, then this is the way we have to take the tensor product. So if it is a state, the electron in the second atom will be in the ground state. Then we can write the state is 1, 0. So finally, okay, now they are interested to measure the position momentum of positron as well as the electron. Okay, at the same time, we have to measure the both position and momentum. So what they have considered, they have first measured the position of electron on one side, and the momentum of they have measured the position of electron and the momentum of positron. Okay, so here we have, so if you exactly know the momentum of the positron, so it is nothing but the opposite momentum the electron will have. Okay, then we can find exactly the momentum of both positron as well as electron. So if you find the position of the electron at the same time, so from the relative position we can find out exactly the position of positron. Okay, then from this gamma decay experiment we can find the exactly the position and momentum of quantum mechanical particle of positron and electron. So generally, the quantum mechanical principle xpx is equal to I h cross. That means we could not measure the position and its momentum accurately simultaneously. Now the things from the experiment, we can measure the position of electron and position and momentum of electron, as well as the position and the momentum of the positron. Okay, so here what happened? This uncertainty principle becomes a failure one. Okay, so you just imagine about the failure of uncertainty principle. If uncertainty principle is failure, what will happen? So the entire quantum mechanics will fail, the nuclear physics will fail, spectroscopy and other in some of the condensed matter experiment, many of the concepts will be failure in the physics. Okay, so due to this experiment, they started to our quantum physics started to grow in exponentially. Okay, after that, the John Bell, after 30 years, they have introduced a non-locality. So that in based on this same again this local realism, they have identified this set of inequality. Again, he demonstrated another experiment. Now we can consider the two particles. So the two particles having the different physical properties. And if you measure the physical properties, the outcome will be either +1 or -1. So if you consider the combination of different observables, finally we will get either +2 or -2. That means whatever if you property measure, so the outcome result is either +2 or -2. Okay, it cannot be beyond +2. Okay, then so they give the Bell inequality is the expectation value of the different physical observables. So that is always it is equal to or less than 2. But after some physical observable, if you measure the spin observable in quantum mechanical observable, so in the state, so this is the state, it is called one of the entangled state. So if you measure this entanglement property, so what will happen? So the finally we will have the 2√2. It is greater than 2. Okay. So what do they have? They have demonstrated if you have any system, if you disturb if you measure the system, we could not measure the quantum physical property of any quantum mechanical system without disturbing. That's why if you want to describe the dynamics of car, we can describe without any disturbing the car. But in order to describe any quantum mechanical property, like for an example, if you have an electron is revolved in the elliptical orbit or circular orbit, so in order to understand the dynamics or the position of electron, so we have to disturb the electron. From that disturbance only we can understand the dynamics or the position of the electron. So due to that position, the disturbance, what will happen? So again, due to the von Neumann collapse postulate, the state of the electron will be changed. Okay, if you measure the position at that time, what will happen? The state of the electron will be changed, the momentum will be changed. Okay, then finally we could not measure the position and momentum accurately. Okay, so this conclude that. So what will happen? This locality and reality is not at all applicable for the quantum mechanical world. Okay, that means if you have any subatomic particle, we could not measure the system with realization with realistically. That means without disturbing the system, we could not measure any physical property of the quantum mechanical system. So that is the concept they have introduced by the Bell with the help of this inequality. The same concept it is also explained by the Schrödinger with the help of local hidden variable theory. And these are some examples for the entangled state. So if you that entangled state, it has a useful for the resource processing task. And these are some. So how long time I can have? So
Sir, it is almost 3:50. More than half an hour is there, sir. You can.
Okay, sir. Okay. Okay, so this is how the techniques how we can find out whether the state is entangled or not. Suppose if you have a state, a bipartite state A, B, C, D, then if you find the product of A, D, and B, C, if are equal, then the state is unentangled or it is called a product state. So, for example, if we have a ket 0, 0, we have the state matrix representation is 1, 0, 0, 0. Okay, now if you want to find the product of A, D, and B, C, in both the cases it will be 0, then it is called a product state or unentangled state. Okay. Similarly, if you have the another one case, if you 0, 0, 0 plus 1, 1. So in that case, if you find the product of AD and the equative BC. In all the cases, it is not equal to AD not equal to BC. Then this kind of states are called entangled states. So the next one is the most important concept in entanglement theory is called as schematic decomposition. So this is another concept of how we can identify whether the state is entangled or not in exclusively for a pure states. Okay. So here the psi is the two particle state. So here we can write as a sum over I lambda I ai bi. So this use the entangled quantum state to improve the speed up of the machine. Okay, after taking the multiplication, we will have the initially it is a 2-qubit state. Now it has become a 3-qubit state. Okay, now we have to do this C0 operations on this. So we have to give this C0 operation on the Anu qubits. Okay, so what will happen if you apply the C0 get on the Anu qubits is to become a superposition qubit. Okay. So it will create the superposition qubit. So whenever we have the Anu's qubit, it is becoming a superposition qubit. So if it is 0, it becomes a get 0 plus 1 by square root 2. If it is get 1, it becomes get 0 minus 1 by square root 2. So then finally we have, so then Anu take the measurements. So suppose in Anu basis, whenever we have the get 0 and 0, so that is, it will choose the identity measurements. So if it is the Anu basis with 0 and 1, we have to choose the Pauli sigma x operation. So if it is 1, 0, we have to choose the z operation. If it is 1, 1, it becomes the x and z operation. So if you taking the measurements on Alice Anu qubits, what will happen? The Bob qubit will be changed. The changes will occur in the Bob qubit. That depends on the changes in the Bob qubit. The Bob will realize what kind of information or what kind of message the Anu sending to Bob. Okay, so from this we can identify this qubits. So this unknown information, it will transfer to the Bob. Okay, so this is the protocol. We can transfer the from one place to another place. So first we have to share a common entangled state. Then we have to combine the unknown message to the entangled state. Then we have to apply the controlled not to the first qubit. Then we have to apply the God mod gate. So finally we have to take the measurements on the first qubit. The measurements on the first qubit will affect the second qubit. That second, from that changes, the Bob will measures his pair and get the unknown message. So this is the way we can transfer the message from one place to another place using the entanglement. So with this, I am stopping. Once again, I thank the organizer for giving this great opportunity. Thank you and everyone for listening this my lecture.
Thank you, sir. Thank you very much.
Thank you, sir.
So even though today's lecture is about the entanglement and applications, but you have covered almost all the fundamentals, sir, all the fundamentals and principles, particularly linear algebra, which are essential to know the entanglement. And along with entanglement, also you have covered the remaining fundamentals also, sir. It's very nice and
Thank you,
informative session. This one is definitely. Thank you very much, sir.
Thank you, sir.
Sir, please stay for the valedictory function, sir.
Yeah, yes, sir. Yes, sir.
It is going to start now. Please stay in the.
Okay.
Call,
Yeah,
sir.
shall I stop my sharing?
Okay, sir. Okay. So now I request Mallikarjun sir, my colleague, please give a special thanks to the today's resource person on behalf of our department. Mallikarjun sir, please give a special vote of thanks to our today's resource person.
Sir, good evening to one and all, sir. I am S. Mallikarjun, Assistant Professor, Department of Physics, Bapatla Engineering College, Bapatla. Sir, on behalf of the Department of Physics and participants, I express my heartfelt thanks to today's our resource person. That sir, meaning was sir that you have covered all the topics from the basics to the applications. Actually, we know very well that quantum mechanics is something like a tri subject, and it is coupled with the practical applications, computer applications. But we know the pain how you have prepared for delivering this one. This clearly we can feel the importance, sir. But all these lectures we can get benefit once we have some books on this quantum computing. Then only many number of students or otherwise faculty can really get the benefit. This is my open opinion, sir. This is my heartfelt opinion, because whatever we know from the this type of lectures, FDPs, we are unable to get something. We are unable to get something because one may not get the quantum mechanics concept clearly. All the persons those who are attended. So once we have any book from any lower standard to higher standard, then all these informations are reached to our doorstep, sir. This is my only help. My personal opinions that I'm sharing, because you have presented excellent information, but we need to get all this information. It is only possible by going through the fundamentals of the quantum mechanics and how we can relate the quantum computing. Definitely, by listening this type of lectures and from this the esteemed resource persons, definitely we can reach to that extent, sir. I sincerely express my thanks to our department colleagues and participants for making this program success, and special thanks once again to today's resource person, sir. Thank you, one and all, sir.
Thank you, sir. Thank
you very much, sir. Thank you, sir.
Participants are requested to is a time for questions and answer section.
Yes,
please, it's very brief. So time is not so much for us. So if anybody raise your hand to ask the question directly, the resource person, any participant there for to ask the questions. Sir, one resource.
Yes, sir. Yes.
Sir, participant can raise your hand.
So there are two persons, Sriram, Lakshman Rao.
Sriram, sir, please raise your question, sir.
Hello, sir. Good evening, sir.
Yes.
Sir, my doubt is, sir, if you take a physical system of two energy levels, generally we know that when an atom is in the ground state, we give some energy to set.
Yes, sir. Great.
Sir, very nice session I heard from you, sir. But a deep subject. But I have a small question. Is it possible entanglement in between ferrous and non-ferrous metals? Entanglement based on that qubits. Just
for that we have to look into the structure of ferrous metal and non-ferrous metals, sir. That's we can directly say that we have. If you know the structure of and alignment of spins particle, from that we can identify, sir. So for that we have to understand the nature of spins of metals. So if it is the metal, the spins are aligned in all the spins are in the same direction. That could be a product state or separable state. There is no entanglement.
Entanglement. Sir, possibility is there. Possibility is there.
Yes. If there is the interaction between the spins are in non-differomagnetic region or non-differomagnetic space, then we have entanglement.
Entanglement. Okay.
ferro or ferrimagnetism, that kind of a structure, we have the unequal magnitude of spin component, then we can realize the entanglement.
Oh, okay. Thank you, sir. Thank you.
Okay, thank you, sir.
Thank you very much, sir. Okay, now it is okay. Are there if any participants are there to raise the question? Sir, Balakrishnan sir, right?
Yeah, yes, sir.
Good evening.
Sir, okay, sir. Okay.
Yeah. Thank you. Technician, thanks a lot for a nice talk.
Thank you, sir.
Yeah. So I just want to have a couple of questions. One for the audience sake, the other one for my sake.
Yes, sir.
So the audience point of view, okay, in the teleportation process, actually we are investing entangled state, right?
Yeah, yes, sir.
So at the end of the day, by investing entanglement, we are going to exchange the unknown qubit from one
unknown qubits. Yes, sir.
Right. Okay. So, okay, in case if I increase the scale, for example, I want to transmit 2 unknown qubits.
Yeah, yes, sir.
How many entangled pairs I require?
So minimum 2 entangled pair is enough, sir.
Minimum 2 entangled pair. Okay.
Yeah,
okay.
yes.
So accordingly, we can decide. So how many unknown qubits I want to transfer? Accordingly, I can decide.
Yeah, yes, sir. For 2 unknown qubits also, 2 entangled pair is enough. Right. 1 pair of entangled.
Correct. Okay, fine. The other point is to come to the conclusion that the given pair of quantum states are entangled. We have to do the Bell's test, right? Bell's inequality test.
Yeah, yes, sir. Actually, that Bell inequality test is applicable only for pure states. Some of the mixed entangled states are not.
For our online faculty development program on quantum technologies, emerging trends in physics and computation. Over the past 3 days, we have embarked on a remarkable intellectual journey, one that has taken us from the classical foundations of computation into the fascinating and transformative world of quantum mechanics. We explored qubits, superposition, quantum algorithms, entanglement and its applications, and the rapidly evolving landscape of emerging technologies that are reshaping our future. This program was not merely about the learning new concepts, it was about the expanding perspectives. Quantum computation challenges the very way we think about information, logic, and problem solving. I sincerely thank our distinguished resource persons who shared their expertise with the clarity and passion. All of you have truly inspired us to integrate these cutting-edge advancements in our teaching, research, and innovative practices. During these sessions, I found myself reflecting on 2 guiding principles. First one is never give up, a reminder that the path of innovation is often challenging, but persistence is the key. Then another one is a teacher is only a teacher if he is a student. As educators, our responsibility is to remain perpetual learners, staying updated to prepare our students for the challenges of tomorrow. I follow these principles myself, and I believe that if you all embrace them, we fulfill the real meaning of this FDP. That more than a single technical concept would be the true key takeaway from this entire event. To all the participants, I congratulate you for your enthusiasm, active participation, and intellectual curiosity. Your engagement in discussions, thoughtful questions, and collaborative spirit have made this program truly vibrant and meaningful. Faculty development program is not just about acquiring the knowledge, it is about transformation. And I am confident that each one of you leaves this program better equipped to guide the students into the future of quantum technologies and interdisciplinary innovation. We are truly overwhelmed by the response to this program. We received 550 registrations. It will be heartening to see approximately 200 dedicated participants actively engaging in every session over the past 3 days. At the outset, I consider it my foremost duty to express my heartfelt gratitude to our magnanimous management for the constant encouragement and support in organizing meaningful academic programs. I also extend my sincere thanks to our esteemed principal, Dr. B. Srinivasrao sir, and our former principal, Dr. N. Ramadevi madam, for their valuable guidance, encouragement, and unwavering support in conducting this FDP. I also extend my heartfelt gratitude to organizing committee for their meticulous planning and tireless efforts in ensuring the smooth and successful execution of this program. In closing, I once again thank all the experts, participants, and organizers for making this FDP a grand success. I wish you all continued growth, research excellence, and meaningful contributions to the academia and society. Thank you. I hereby declare this FDP on quantum technologies, emerging trends in physics and computation formally concluded. Best wishes to all. Sir.
Thank you, madam. Thank you very much. Now it is the I request the participants, please give your valuable opinions and suggestions, if any, about this national FTP, quantum technologies, emerging trends in physics and computation. And I first our department former HOD Dr. K. Ramakrishna sir. He's on the journey. So with the problem of net, sir send a message send a message. I will read the message about which is sent by our former HOD Dr. K. Ramakrishna, alumni of Benares in the University of Varanasi. So message is as follows. It is very pleasure to say a few things of this FDP. The three speakers exceptionally illustrated the past, present, and futuristic aspects of quantum computing. Starting with the fundamentals of quantum mechanics, they explained qubits, superposition of states, digital gates, quantum gates, algorithms, and new applications. Yes, it is indeed, it is a milestone for the learners and created an enthusiasm to learn more and more about quantum computing. I am extremely thankful to the organizers and the teammates of Department of Physics. All the very best. Thank you, KRK sir. Thank you very much for your message. Even though you are busy, thank you very much, sir. And I request all the participants, if anybody give your opinion, please give about this FTP. Participants, please raise your hand. We will, our admin will give you the mic and permission. You can give your
Sir, good evening, sir. This
response
is
and
Sriram.
opinion. Sriram is there. Sriram, sir. Okay.
Yes, sir. I am very much thankful to the speakers for their inspiring lectures.
Sir, open your camera also, sir. Sir, please open your camera.
Sorry, sir. This
You are
camera
audible,
is
okay?
not, camera is not working properly, sir.
Not
Sorry.
no problem, sir. This
Yes, sir. Yes, sir. Their depth of knowledge, their clear explanation, and their interactive approach made these concepts easy to grasp, sir. And it is motivated the participants to explore this domain further also. Because here I am also teaching the quantum computing paper to my students. So many doubts I clarified in this FDP, sir. So that is very, very, very thankful to my speakers. So thank you, sir.
Thank you very much, sir. Any participants are there? Please give your opinion. Participants, please raise your hand. Admin will give your permission to mic and camera. Okay. So participants are requested to camera. We take a photograph of the overall as a token of record.
Amarnath sir. Please unmute your mic, sir. Amarnath sir.
Amarnath sir, please unmute your mic and say something about FDP, sir.
Thank you for the wonderful session, sir. Actually, in this days, studying this quantum technologies based on this are difficult to understand. So these sessions are useful for us, sir, as a faculty. And if possible, can you provide the PPT, sir?
Definitely, sir. If the resource person shared it, we will share it to the WhatsApp group. No problem.
Okay, thank you.
So participants,
Sir,
please open your camera. We take a photograph as a token of record. So remaining participants, please open your mic, sir.
Sir, good evening.
Sir, mail those, sir. It will take us almost maximum 1 week around. We will mail to you. Thank you all the participants. Thanks for participating with this FDP. I hope you are learning very much and